Hello, Mr. True, again. Now, in AP Statistics, I've been talking about normal distributions. I've finally defined what that means using the empirical rule and showed you how to use the normal probability plot to check for normality. So, I've been talking about z-scores, or standard normal calculation, standard normal distribution. Now I've got these bell curves all over the place and I've defined what normality is. Let's actually tie the two together and see how the z-score calculation, which is estimate minus parameter over the standard deviation of the estimate, actually works. Now, this is very early in the book, so they're just kind of spoon-feeding us all the information. So this formula is going to look like this. X for the estimate minus the population mean that they tell us and the population standard deviation that they tell us, because we don't really know how to find any of this stuff yet. And I'm going to just try and run through in the next 15 minutes as many z-score calculations as I possibly can. We are going to be ending with a p-value, which is the probability of observing a certain event, or one that's more extreme, which means they're all going to be inequalities. And don't forget, our density curves have an area of 1. And the reason why is because we can take that area that we get out of the bell curve and easily convert it into a percent by just moving the decimal over 2 places, and that'll be the probability of observing whatever event that our word problem might actually be talking about. Well, I'm going to give you some just generic data. We have a normal distribution. Did I even write that? No, I didn't. We have a normal distribution that has a mean of 200 and a standard deviation of 30. Voila! Bell curve, center at 200. Z-score calculations. Every single problem that gives you or says that a distribution is normal and then asks you for the probability of an event or what proportion of data lies within some interval, all questions like that will be followed or worked with the z-score calculation. We will learn other variables such as the discrete random variable that may not be using that z-score calculation. But if you hear normal and then proportional probability, that will be a z-score calculation. And again, these are on univariate quantitative data, that data that's along the x-axis. We're not talking about scatter plots and regression lines or chi-square, which we'll talk about at the end of the year. Just one nice set of data that's quantitative and continuous along the x-axis. So let's answer some questions. Like, what is the probability in this distribution with a mean of 200 and a standard deviation of 30 that x is less than 155? Okay, well, I have 155 here, and I want to find the area to the left of that value. So I'm going to do z equals the statistic, which is what the question is about, minus the parameter over the standard deviation of the statistic, which is 30. That comes out to negative 1.5, and I forgot my book. All right, with your table in the front of your textbook, and I know you can't see this on the camera, but hopefully with your book you'll see enough to follow along. My z-score is 1.5 or negative 1.5 standard deviations. It's negative because my value is to the left of the mean. Z-scores are negative to the left of the mean. Negative 1.5. So, the front page of my book where the negative z's are, I'm going to go down to negative 1.5, and I don't have a hundredths place, so I'm going to use the first column. Negative 1.5 has a p-value of 0.0668. So my p-value is, from this z-score, 0.0668. That means that roughly 6.7% of my data is less than 155, or I would have a 6.7% probability of observing a piece of data or observing an observation of less than 155. Don't forget, the unit of z-score is standard deviation. So this is 1.5 standard deviations to the left of the mean. So this answer came out to be 0.0668. I'll need to erase these examples as I go because I didn't give myself very much room to do these examples. What is the probability that x is less than or equal to 155? Well, if this is a continuous random variable, the probability of getting exactly 155, the probability that x is 155, is 1. That's one specific outcome, and if this is continuous, there's an infinite number of possibilities. Well, 1 over infinity is 0. When you're talking about bell curve calculations, the probability of observing one specific outcome is always 0. So, the probability of observing a value less than 155 is the same as the probability of observing 155 or less. So you have to use the proper notation for the wording of your question, but it will not change your answer. Bam! All right, moving on. Let's take a look at another value. Let's say that I want the probability that x is less than 228. Well, 228 is over here somewhere. This is just a sketch. And I want to find the area to the left of 228. So I'm going to be looking for this area all the way on the left-hand side of this bar graph, or excuse me, normal density curve. All right, well, normal, probability, that means z-score. And notice these patterns. I'm giving you the x's, we calculate the z, and we do the p-value. We're going to do the reverse in a minute. So z equals 228, the question, minus the parameter, which is 200, divided by, this is the center of the bell curve, divided by the standard deviation of 30, and that gives me a z-score of, drum roll please, 0.93. And on your z-score chart, on the part that has the positive z's, you go down to 0.9 on the z column, go over to the hundredths column of 3, and you'll find your p-value. The area to the left of this z-score of 0.93, the area to the left of 228, is equal to 0.8238. Okay, now, what if you want the area of an interval? What if I want this area, just between 228 and 155? Well, if you want the area of an interval, it's the area to the left of the large number. That's how you take it out of the chart in your book. You take the area to the left of the small number and you subtract them. I want to take out this area and that I had in the green. All of this area is 0.8238. I want to cut out that little tail and just have the interval left. So I'm just going to do subtraction. I'm just going to cut it out like a pair of scissors or a minus sign. So the probability that x is between 155 and 228 is 0.8238 minus, now when we take out this little tail with subtraction, 0.0668, or that's 0.757. So the probability of observing a value between 155 and 228 is 75.7%. Awesome. Okay, a couple z-scores and how to find the area of an interval. Area to the left of the large minus the area to the left of the small. Now, what if I want this area? What if I want the area to the right of 228? What if I want the probability of x being greater than 228? Or let's just throw an equal sign in there for good measure, because it's not going to do anything anyway. You just have to match the wording of your question. To the right of 228, if this is a density curve, and I'm focused on this green area, all of this, which is 0.8238, how much is on the other side? Well, if it's a density curve, the area has to equal 1. Well, if the left side is 0.2838, the right side has to be what? 1 minus 0.8238. And I will be doing a video to show you how to use your calculators to get these numbers as well. I'm doing all these calculations as if we're reading a chart. Okay, let's see. Do I have time? Oh, I got plenty of time. All right, thought it was running out. I got 5 minutes still. So, keeping with, I'm just cleaning this up because I got too much stuff going on here. What if I ask you, what is, let me get my distribution back up here. We have a normal distribution, again, with 200, So 200 dead in the center, and a standard deviation of 30. By the way, if I was doing a quick sketch of this normal distribution, because of the 68, 95, 99.7 rule, I could put tick marks where my standard deviations are, and that would be 200, 230, 260, and 290, 170, 140, and 110. You would have to draw it this way if you put the tick marks every standard deviation, because within 3 standard deviations left and right, that's 99.7% of your data. Okay, at any rate, all this stuff is going to make my drawing look a little bit complicated, I'm sure. I want to know, within this distribution, what is the third quartile? What's the 75th percentile? Where is Q3? Now I'm going back to this. You're either given a statistic, which you then find a z-score, and then the p-value or the area under the curve, or they simply work in reverse. If I'm giving you or asking you for Q3, I am telling you what I want shaded in the bell curve, and I want the statistic. I want the x. Q3, third quartile, 75th percentile. That means, and percentile is what? What percent of data is below the observation you want to look at or discuss? So somewhere there is a number whose area to the left is 0.75, the third quartile. And I could be asking you for the 90th percentile, the 10th percentile, the longest 25th, the longest 25% of the values. If this were some question like, I don't know, length of pregnancy or something like that. But where is Q3? All right, enough talk. I'm going to run out of time if I don't stop talking. So Q3, well, if my p-value is 0.75, I'm going to take my z-score chart and look in the body of the chart, because that's where the areas under the bell curve are. I'm going to look in the body of the chart and find as close as I can to 0.75. So if I do that, your z-score is going to be, that'll give me a z-score of 0.67. So this statistic, which we're about to find, is 0.67 standard deviations to the right of the mean. Now if I know what the z-score is, guess what formula I'm going to use? Area? No. Perimeter? No. I'm going to do the z-score formula, which is z equals x minus mu over the standard deviation. Well, my z is 0.67, my mu is 200, and my standard deviation is 30. If I multiply both sides by 30, I get 20.1 equals x minus 200, and if I add both sides by 200, I might just finish on time. And my statistic, my 75th percentile, my Q3, is 220.1.